So the second half will be a bit different, be a bit less like a math talk, I guess. And again, I'll keep here I'll keep things a bit higher level, but feel free to ask me questions. Let me start with one clarification. Maybe I misunderstood one question from before we took the break about whether the things I said only hold in finite dimension. So the results that have like D in them don't usually make sense in infinite dimensions. But the LP embedding into Euclidean space or L1 with distortion order of P, that can be stated for like the function space is LP. Like that doesn't have to be in the finite dimensional setting. Like it all kind of makes sense. Good. All right, so the goal for the second half, and maybe it will be a shorter one, although not the best at timing, but I'll let you go before lunch for sure. Right, that's the plan? Lunch? Like noon, I mean? Lunch can be whenever, right? But noon. So the plan for the second half is to tell you about one application of average distortion embeddings to constructing data structures for near-neighbor search. I said here, the specific thing I'll talk about is based on work with two University of Toronto students, Dipanshu Kush, who this was like it's like a side project for him. He really works on like algebraic complexity. Yeah, and Hao Hua Tang, who's now my PhD student. But really, results are based on a lot more work, including some joint work with a bunch of people here in this room, with Eric, with Aleksandar, with Asaf Naor, with Ilya Razenstein as well. And you'll see these things mentioned as I talk. And this is a nice picture of a space partition from a Quanta magazine article that I borrowed. Okay, so now, yeah, let's now talk about something a bit more algorithmic, particularly about very classic data structure problem. Again, the first few slides are probably like very familiar to everyone, but I want to make sure we all are on the same page. So here's the nearest neighbor search problem. This is the exact nearest neighbor search problem, in which we're given, so yeah, I won't try to give a lot of motivation on why this is important. This is a very important computational problem used for all kinds of things, like it's useful in all kinds of data analysis, machine learning, it's like useful in databases, information retrieval, like it's all over computer science. It's a thing that people really like to be able to do fast. So what is the thing? Here's the static version of the problem. I give you endpoints that I'll call P from some metric space. Okay, and then your task is to pre-process these endpoints into some data structure that hopefully doesn't take too much space, and that allows fast query time. And what is a query? A query is just another point from the metric space, and you want to find the closest, which I'll call Q. You want to find the closest point to Q in your data set P. Okay, so you want to find a point in P that minimizes the distance to Q. This is the exact nearest neighbor search problem. Here is a picture. Oops, okay, that has the picture. So the green points plus the purple point are the points at P, and Q is the query point. Given a query, I want to find the purple point in this case. Okay. And the things we care about as kind of all data structures, at least all static data structures, is pre-processing time. So how long it takes to pre-process P into a data structure, the space the data structure takes, and how quickly we can answer a query. Okay, what are some things you can do? You can just store. This is like, you know, I teach data structures, and I always ask these like second-year undergrad students, like, what is the first data structure? It's always like a list, basically. So you can just store P and just go through it one by one at every query. So you can always answer the queries with n distance computations. Takes linear space. Space is amazing. Reprocessing is like essentially non-existent. But answering a query, we're considering to be too slow. So for our purposes, n distance computations is too much time, because typically in applications you want to like solve this problem over and over and over again. So as most data structure problems, yeah, n is too slow. We want sublinear time to answer a query. the more sophisticated things you can do that I won't go into that work well in fairly low dimensions, like 2, 3 small constant dimensions. Basically, you can compute the Voronoi diagram, roughly speaking, of the point set. You can kind of figure out where should the query land so that, okay, so for each point in the data set, you should you can figure out what is the region of queries for which that data point is the answer. Okay, so this is this can and you can do different kind of like partitioning, divide and conquer data structures. There's like interesting results here, but they tend to have at least one of the parameters exponential in the dimension. Okay, so they're not very well suited for high dimensional spaces. They tend to also like, most of the classical work is in Euclidean space, okay, as well. This is, I guess, another limitation. Good. So a major question here is, in high dimensional spaces, so some like arbitrary metrics is too much to ask for, but you know, in as general settings we can handle, and in a high dimensional setting, can we achieve sublinear in the number of data points in our data set query time and polynomial in the space and time? Okay. And there are some strong hardness assumptions you can make that, however, for all we know are true. Things like the strong exponential time hypothesis, under which this goal is not achievable for this problem. Okay, and this is one very concrete example of the curse of dimensionality. So again, as far as we know, it's impossible to have a data structure that takes polynomial in n and d space and answers queries in polynomial in d time and sublinear in n also time. Okay, so as far as we know, these things cannot happen all at the same time. Good. So the usual thing, one of the usual things we do in computer science. Okay. Usually, what we do in this kind of situation, we change the problem. And one of the usual ways we will change the problem is to allow for an approximation. So instead, we solve this problem, which is the approximate near neighbor search problem, where I also have an approximation factor c, something bigger than 1. And actually, I think I kind of compressed things maybe a little bit too much. So the goal is the same as before, except, yeah, so okay, I think I should have included one more slide, but let me explain. So the approximate nearest neighbor search problem is kind of what it sounds like. It's the same as before. It's just that I now allow returning a point that's maybe not the closest point to the query point, but at most c times as far. Okay. So I'm allowed to say c is 2. I allow it to return a point that maybe is twice as far from my query as the closest point. It turns out that in some sense, it's enough to answer an even easier problem where we fix the scale. So this is this approximate near neighbor search problem, where I also give you kind of the distance scale at which will work. It's almost like I'm telling you what is the distance to the nearest neighbor ahead of time, and you can use that in constructing your data structure. Turns out that comes at like little cost. Okay. So here I'm given a data set n points from some metric space n, the distance scale r, and the approximation factor. And I have to preprocess p into a data structure where I can use r so that I can do the following. Given a query, which is q, if it's the case that there is some point, like the purple point here, that's a distance at most r from q, thanks to Eric for that animation right that I've been like carrying through for years. Good. So given the promise that this purple point is at most distance r from q, I want to return some point that's at distance at most cr. If there is no point that's at distance at most r from q, then I make no promises. Okay. So it's in a setting where I have somehow like bounded aspect ratio, some like bounded ratio between smallest and largest distances, it's pretty easy to see that I can like think like Hamming space where every distance is between 1 and d. If I have like d-dimensional strings and I take Hamming distance, that kind of setting, you can just essentially like you can just build this data structure for like powers of 2, like r equals to like powers of 2, and do kind of a binary search type thing. And you can see how this lets you solve the, like read the approximate nearest neighbor search problem where I always return a point that's not much further than the closest neighbor. If you don't have a guarantee on bounded aspect ratio, then this is still enough, but that's a harder thing to prove. But it turns out to be the case. So this is an important result by Indig and Mutwani from '98 that says that if I give you this, I can achieve order of C approximate nearest neighbor search. So essentially the same C factor approximation with not much more space and time. So this is the problem that we actually need to solve. This is all to say basically I can tell you what the scale is. Questions here? Maybe this is all familiar as well to a lot of people that we see. Okay, so what do we know about this problem? Now, like the rest of the talk is about this problem. So okay, last chance to ask a question. Okay, so I don't know if this is not exactly true. Sorry, this is probably a bit of a lie, but a lot of the work here is for L2 and L1, and like for like a small subset of the kind of distances we can consider. This is like a bit of a lie because tomorrow morning we'll hear about other metrics, but there's still a lot of things we don't understand here. Good. So maybe what I should say is like a lot of what we know is about L2, L1, and kind of embeddings into L2 and L1. Maybe that's a slightly fairer statement. So what do we know about like L2 and L1? Here is like one very like classical result. It's not the optimal or the best result, but it shows that there is something we can achieve. So for L2 and L1 and LP between 1 and 2 in general, using something called locality sensitive hashing that I'll explain more in a little bit. I'll say more about what locality sensitive hashing is pretty soon. We can achieve approximation which is say on the order, okay, so for any epsilon is a parameter that you can choose, you can achieve approximation on the order of 1 over epsilon, space which is almost linear, so it's on the order of dn to the 1 plus epsilon, so almost linear space. And query time which is polynomial in dimension and sublinear, so it's n to the epsilon. So think of epsilon as like 1 over 2 maybe, then you can achieve square root of n query time. Okay, so certainly non-trivial, like much better than linear search. Okay, so there's like a long line of work improving these results in different dimensions. The most recent survey, still, okay, relatively recent, of the theoretical work in this space was from 2018. There's a nice survey by Aleksandar, Piotr Indig, and Ilya Rosenstein that explains some of this like big space of things that has been done here. Okay. I should say maybe we'll hear maybe today even about that. There's also some applied work in this space because this is a problem people really want to solve. And the flavor of algorithms people use in practice is a little bit different. And it's an interesting question to like bridge the gaps between theory and practice here, but I'll let Piotr speak more about that, I think, later. Okay, so good. So this is kind of the classical stuff. Let me say a bit more about what locality sensitive hashing is. And then eventually I want to tell you how we can handle things that are not L1 and L2 using average distortion embeddings to give you a flavor of how they can be applied. Okay, so what is locality sensitive hashing? Here's some more parameters. Okay, so it's a natural idea. Then again, it's probably like familiar to a lot of you. So the idea is that we can build a data structure using hashing but we need a hash function with special properties. So we want to be able to find random hash functions that have the property that points that are close collide more often than points that are far. Okay, typically, classical, like second-year data structures course hash functions just try to make sure nothing collides as much as possible. For near neighbor search, we want some collisions because we want to find a near neighbor. But we want the collisions to be more likely when points are close than when they're far. Okay. And turns out that if we have that, then there's a fairly natural way that you can use these things to build a data structure. Okay, so this is again due to indicament 1. So the exact guarantees are the following. We want to make sure that for any pair of points, x and y, again, remember we fixed the scale r. So from now on, r for us is the scale of things being close. If two things are distance at most r, then they're close. Okay. So things that are close, that is distance at most r, should collide, should get the same hash function value with probability at least p1. But things that are far, so their distance at least cr away, so they don't qualify as a possible output to our problem. Things that are far should collide with probability at most p2. Okay, and the more p1 and p2 are different, we want p1 to be high and p2 to be low. And the more they're far from each other, the better our space and time guarantees are going to be. So the important parameter here that measures the distance between p1 and p2 is this ratio of logs. I think the way to think about it is, what is the number rho, so that p1 is p2 to the power rho. So rho here is something less than 1. Think of like, it would be great, for example, if p1 is the square root of p2. These are numbers less than 1, so square root means quite a bit bigger. Yeah, think if this is like, if p2 is 1 over 100, square root of that is 1 over 10, which is quite a bit bigger. Okay. So whatever is the best rho, so that this thing holds, so that p1 is p2 to the power rho. If with that rho we have such a locality sensitive hash function, then we can get a data structure with space which is on the order, I'm ignoring, by the way, here space and time. Like in the space-time, I'm ignoring dimension, but the dependence on dimension is polynomial. So we can get space and time that look like space is n to the 1 plus rho, and time is like n to the rho. And for L1 and L2, one thing that happens to work is you can take a random grid, basically, like just randomly, like pick coordinates and pick kind of a random hyperplane orthogonal to that coordinate, basically like coordinate aligned hyperplanes that divide your space into a grid. If you pick a random grid like this in a like natural way, turns out you can get a locality sensitive hash function where rho looks like 1 over c. C is the approximation factor. And that gives the results on the previous slide, more or less. Okay, so with approximation c, you can get n to the 1 plus c, roughly speaking, space, and n to the 1 over c. Right. Okay. All right, good. Questions?
What about deterministically doing
it? Good question. There is some work. I see. There must be a lower bound in some sense, but how? I guess with algorithms. There's some deterministic data structures. For L infinity, for example, there's a deterministic data structure with log dimension approximation. But for stuff like Euclidean space, I feel like
there are results that would obtain that you have success probability which is 1, but the query time is an expectation.
Right. So there are Las Vegas algorithms that where the running time is an expectation, but you have no probability of like making a mistake or of failing. But truly deterministic, at least I don't know. And I guess like any lower bound has to be kind of in a
you can't have a lower
toy model, right? Yeah.
But why?
Oh, I guess because it's like a computational question.
Oh yeah, so, I see.
We just don't know how to prove these kind of lower bounds. But I guess there would be, I don't know actually. Yeah, good question.
So it's fairly open deterministically?
There must be a lower bound for like deterministic decision trees or something, right? but maybe not sure you don't. The problem is a lot of them you can show in for like something like decision trees that. So the algorithmic data structure is like a deterministic decision tree, and you can try to formalize that, and maybe you can show that that doesn't exist for L1 or L2, and beyond that, I don't know. Does anyone know if it's kind of open? The question is, are there deterministic data structures that work as well as LSH for L1, L2?
Oh, I see. So I think I think you can get deterministic data structure with slight loss of parameters, if I remember correctly. But that also depends what you mean by deterministic, right? I mean, you could have a randomized construction which gives you deterministic guarantees for the query time. But the construction itself is randomized.
I see.
So now whether you call it deterministic or randomized.
I see. Okay. Thanks. Okay. Good. So I'll be focusing on porting this to other spaces, not L1 and L2. So the general question that I think is very interesting is, how does the geometry of a metric space typically affect the complexity of this A and M problem? So there's something here that I didn't mention. So from now on, I'll call this an efficient data structure for A, or like something like this. Basically, when the space is, this would be ideal, but I guess at least polynomial in dimension and hopefully close to linear, or at least polynomial in n, the data set size, and query time that's polynomial in dimension and sublinear in epsilon. So if you fix these requirements, what is the best thing you can say about approximation, and how does it depend on the geometry of your metric space? That's, I think, an interesting question. Here's something that we know. Sorry, this. Anyways, sorry, this slide is too busy. Like, I think my animation broke at some point, so ignore that part. This part is already busy enough. I'm not expecting to remember these slides. I mean, this slide especially. I just want to say there's like some stuff that we do know. So this is based on sequence of papers, like at least, yeah, I'm citing one of them, but in a way, at least two papers with Alex, Asaf, Ilya, and Eric. So basically, there's some stuff you can say about more general spaces. We have approximately linear search data structures with kind of similar guarantees in terms of space and time as locality sensitive hash function, as locality sensitive hashing. They achieve these approximations, these data structures for different spaces. So we have some results for LP and Schatten-p spaces. Maybe the main thing to remember is for LP and Schatten-p, the approximation is in the order of P again, and something that depends on epsilon. Epsilon again is some parameter that determines how quickly we answer queries. And there's some results for any d-dimensional norms. In particular, we have a data structure with this kind of funny approximation for any d-dimensional norm. So this is log d to the power square root of log d. So it's it's, okay, so this function is smaller, like grows slower than any polynomial, but it's also not like log. So it grows faster than we would like, but it is better than applying John's theorem and just applying a data structure for L2. This is maybe something else I should have said. One thing you can always do for an arbitrary like d-dimensional norm space is apply John's theorem and just solve the problem in L2. That gives a square root of d factor approximation, and similar space and time is what we can get for L2, because we're really running a data structure for L2. All of these are better than that. That's the main point, including for any d-dimensional norm. Okay. And this funny thing here is actually like it's related to the last thing that I talked about before the break. Did this slide? Yeah. In a way that I won't quite specify, but it comes from that somehow. Okay, so the technique that we used in these papers was based on locality sensitive hash function, on locality sensitive hashing, but we use, roughly speaking, we use hash functions that can depend on the points at P. And in some sense, that seems to be perhaps necessary. Good. Like, I think that's something you can try to formalize and prove, that you do need your hash function. Like, if you're going to use this kind of hash function approach, you do need your hash function to somehow depend on P. And these results were proved using something called nonlinear spectral gaps, which is like an object that, or like a notion that's, in the sense that I already mentioned in the first part, kind of dual to average distortion embeddings. But because we worked with the dual notion, these data structures were efficient in a funny way. So basically what we could show is that we can sample a hash function from, there exists some distribution on hash functions. We can sample from this distribution in time exponential in dimension. And once we sample from it, we can actually compute the hash function quickly. So in certain, like we do get a data structure where query time is fast and the space is small, but constructing that takes exponential time. And the reason for that was because we kind of work with the dual problem, we basically could only show kind of existence of a good hash function, but finding it like took exponential time. And once we find it, it's efficient to compute. It's pretty explicit, but we don't know how to compute it, like how to sample it quickly. Let me put it that way. Okay. So these data structures all have like exponential preprocessing. Otherwise, space and query time are good. Okay, and they're related to average distortion embeddings. And the main thing I want to tell you, like before lunch, is that you can essentially get these results all explicitly from average distortion embeddings. So originally this was kind of implicit in the original work, but more or less this connection can be made more explicit. And these results can be all seen from kind of a general connection that shows that if you have an average distortion embedding, you can get an approximately a neighbor search data structure from it. In particular, you can get a data-dependent LSH construction from the average distortion embedding. So this gives some results where the data structures actually can be also constructed efficiently. And these results we had with these two students, Dipanshu Kush and Hao Tang. So at least for LP spaces and for some of the Schatten-p spaces, for p less than 2, we can construct approximate nearest neighbor search data structures with kind of small approximation, and everything is efficient. So preprocessing, it's polynomial time, space and time are what we would like them to be. So for LP, we achieve kind of order of p approximation and constant approximation, basically, for Schatten-p for p less than 2. Okay, this is, again, all like much better than you can get from John's theorem. And for LP, for p bigger than 2, prior to this like sequence of work, there was nothing known that's like that's this good, that has like approximation that's even polynomial in p. Okay.
So, sorry, could you clarify the relationship between this and the previous slide?
Yeah, it's a little, so the main thing that's different in terms of like the papers is that this one, for some of the things on the previous slide, here we can get data structures where also the preprocessing is efficient. Okay. It's polynomial time.
So the results from the previous slide are all from average case?
In hindsight, you can get all of them from average distortion embeddings, although that's not super obvious from the way the paper is written. But in hindsight, they also all follow from average distortion embeddings. So this like preprocessing versus query time thing is related to what I was saying before the break, which is that for these average distortion embeddings, sometimes like choosing the function f takes exponential time, but once you choose it, you can quickly evaluate it. Yeah, so that's exactly, so choosing the function f in a data structure application happens at preprocessing and can take exponential time. But once you choose it and you write it down, you can quickly evaluate it. And that's done at query time, and that's efficient. And that's kind of the issue that is like that's the same issue basically here with the data structures as well.
So the first bullet point is a consequence of the map you showed us before the break.
More or less, yeah. Plus a reduction, yeah. So the first bullet point, good, thank you. The first bullet point is a consequence of the map that I showed you before the break, plus a reduction. So there's a general reduction that we can show that I'll tell you about on a high level. That basically, if I have a metric M that embeds into, let's say, L1, so L2 is enough because L2 embeds into L1 with constant distortion. But kind of the weakest assumption I can make is embedding into L1 with average distortion D. That gives an efficient approximate linear search data structure with almost the same approximation. So with approximation, that's almost the same as the distortion. So in general, you get from D to D log D. And if the embedding is efficiently computable, then the data structure is also like is efficient. Okay. And in particular, if you can efficiently choose the embedding function, that means efficient preprocessing. If you can efficiently evaluate it, that means efficient query time as well.
What happens with dependence on epsilon in this general reduction? Because you need something about the inverse of the mapping. It's a modulus of continuity. Or?
You mean like that happens in the construction of the embeddings, I think.
What happens with the dependence on epsilon?
Like this epsilon, right?
Yes, 1 plus epsilon approximation.
1 plus epsilon approximation, like, do you mean the epsilon that goes in like query time and space, or is this a different epsilon?
At least in the approximation, in the Schatten-p p less than 2, you had 1 over, let's say p equals 1 over epsilon squared, not 1 over epsilon. What's the meaning of the square?
Oh, here?
Yes, p equals 1.
Yeah, I see.
How does this go into the general reduction?
Good. The thing, yeah, I think the thing I'm good. So the thing that's missing from the slide is for Schatten-p, the embedding is of a snowflake. Right. So in general, the dependence on epsilon is always like 1 over epsilon, I think. But let me see. Right. But because we're embedding, like, let's say for Schatten-1, we're embedding a half snowflake, things get squared when you care about the original Schatten-1 distance as opposed to the 1/2 snowflake of the Schatten-1 distance. So this comes from using like a snowflake.
So that's the modulus of continuity. So it's not.
That's from the modulus of continuity when you're constructing the embeddings, yes.
But it does not influence. I see. So the distortion, the D will just become D squared or something.
Yeah.
Okay.
Right. In other words, like for Schatten-p, I'm not using this result. For Schatten-p, I'm using it for like a snowflake of Schatten-p, and yeah, basically. But right, the modulus when the modulus of continuity is when I have alpha holder continuous stuff then things get raised to like 1 over alpha. Okay, so in what time I have left, I want to tell a little bit about how this reduction goes. So once I have this reduction, that more or less gives me this result for LP plus what we did before the break. You might ask, okay, before the break I showed you embedding with average distortion P or order P, and now I'm saying, well, average distortion D means a D log D approximation for approximate near neighbor search. Yeah, and in these results I'm skipping the dependence on epsilon a little bit. It is 1 over epsilon is the hidden dependence on epsilon there. So there's this extra log D factor there that doesn't seem to be here, and the reason is for LP you can do something a little bit special and not have the log. So be a little bit more careful. But this is the general result that I know how to show at least. I don't know if this is tight in any sense. I haven't thought about that. Questions? So let me tell you how the general reduction works. It's more or less how you would, I think it's more or less the natural thing to do, plus some places where you have to be careful. So first, let me be a bit more specific by what I at least will mean by data-dependent LSH. So remember LSH, the definition of a locality sensitive hash function asked us that close points have probability at least P1 to collide, and far points have probability at most P2 to collide. Okay, now I'll ask something else that's a bit more in the spirit maybe of average distortion embeddings. Kind of. I'll ask that, it looks quite different, but there is a connection to the original LSH that I'll show in a second. So what I'll ask is that, okay, so again, this guarantees for any 2 points in my metric space. If their distance at most P1, if they're close, then they collide with probability at least P1. At the same time, for my points at P, so this is data-dependent LSH, so the definition is with respect to points at P. For my points at P, I want to make sure that points get roughly distributed. In particular, no bucket of my hash table. So if I hash the points in P into a hash table using this hash function, no bucket should get more than P2 fraction of the points. Yes?
And is this a bound on the expected value of each bucket, or it's a strict bound?
At least when we did this, it was okay to ask for this to happen with probability 1. For our parameters, this was not like an issue. But I think if you do it in expectation, nothing really breaks too much. The reason was like, okay, we guaranteed it in expectation, but then we could also show that it happens with constant probability, and then we could resample without things changing too much. So it wasn't a problem. Good. Okay, so this is what I call data-dependent LSH. So close points close points collide, with good probability, but I never collide too many things into one bucket. Okay, that seems to be like nonsense, right? Because if all the points are close, they will all collide, right? I mean, not all, but if all the points are close, I have a lot of collisions. So some bucket will be heavy. This doesn't make any sense, right? So for this to make any sense, I can only require this to hold for dispersed point sets. Okay? Point sets where no ball of some big enough radius contains more than half of the points, let's say. And you can parameterize the definition. Instead of half here, I can put like a parameter. But in these slides, I'll keep this fake. In the paper, we do parameterize it. But yeah, for now, let me say this is the definition of dispersed. I'll say that, so CR here is not an accident, right? Like C is my approximation ratio. So this is the distance between far points. And I want to make sure that basically most pairs of points are far. And one way to say that is that no ball of radius CR should contain more than half of the points at P. Okay. Now, if I put this restriction on P for dispersed points at P, this definition hopefully can make sense. Yeah, and I'm claiming really LSH, regular, like Indic Mutwani LSH, implies this data-dependent LSH with like similar parameters in the way you would expect. Basically, if I have if I have like regular LSH with the usual guarantees, and if I have a dispersed point set, then I'm claiming that more or less I will satisfy this definition. Why? Because P being dispersed means most pairs of points in P are at least distance CR apart. Okay, because no ball contains too many points, so most pairs of points must be far. Okay, but this is a bit like inaccurate. So at least P2 fraction of the pairs of far points will be separated, at least in expectation. So at least in expectation, this guarantee will be roughly satisfied. Again, I'm not doing the exact math, but the idea is because P is dispersed, most pairs of points are far. And if I pick a regular LSH function, this means the P2 fraction of the pairs of far points will be separated. So if I do things carefully, I should get that no bucket in my hash table is like too heavy. Kind of makes sense. Okay, good. So far I introduced some definition, and I said, okay, if I have a regular LSH, then this is satisfied. Good. So why is that helpful? And the reason that's helpful is that I can kind of preserve these guarantees under average distortion embeddings. Okay, sorry, this is just what I get from, let me back up for a second. Just from like this observation that regular LSH applies to an independent LSH, basically tells me that for L1, for example, I can get some trade-off between these P1 and P2 parameters. And it's the same trade-off as like regular LSH. So this is just something that we use. Okay, now what's useful about this kind of data-dependent definition of LSH is that I can use it together with average distortion embeddings. Okay, good. So this is the idea of the data structure. So, okay, this is like one idea. It doesn't explain the whole data structure, but this is one idea. Suppose I give you a point set that's somehow dispersed. If it's not dispersed, we'll see what to do about that later. Okay, it's easy to deal with that part actually. But let's say P is dispersed. Those tend like end up being kind of the hard point sets to deal with. So if P is dispersed, then the idea is to get a data-dependent LSH for P, which now is in some metric space that's not necessarily L1, by first applying some embedding to P, and then using the L1 data-dependent LSH on like f of P. Okay, so we take our points at P, we embed it into L1, we basically apply the regular LSH random grid construction after mapping to L1. And then I see how that partitions the original point set. So in a way, I'm thinking about the inverse of this embedding that's like, looks like some funny partition in the original space. But it's really implied by the embedding plus how I partition things in L1. Okay. So the hope is that if this F is like nice enough, then doing this gives me a data-dependent LSH in the original metric. Okay. And I'm going to claim that nice enough is something that we can get from average distortion embeddings. It's not exactly the same, but it's not exactly the same thing that we need. So what do we need, right? So for data-dependent LSH, one thing I need is that points that are close have good probability of colliding. Okay. So let's think about this. Let's take 2 points that are close in the original space. I now embed them with F, and I partition after the embedding. Okay. So if my embedding doesn't expand distances too much, then points that are close here are somewhat close there. And I know from the guarantees of like regular LSH and L1 that points that are like somewhat close here have reasonable probability of colliding. Okay. So in one direction, it's definitely enough to just not expand distances too much, which is like not surprising, right? Like usually all these things are like preserved under bi-Lipschitz embeddings. However, I think what's more interesting is like kind of the other part of the guarantee, which is that again I want to make sure that no that no bucket here, no cell here gets too many points, right? This is the other thing that I need, like more than P2 fraction of the points. And we said this is true here if there is no dense ball, if this point set is dispersed. Okay. But I only know that this point set is dispersed. So what I need from F is that it maps a dispersed set to a dispersed set. So if there is no ball here of radius CR that contains more than half the points, there better be no dense ball here. Better, like most pairs of points here better be well separated. Okay? And if I have that, then I would have a data-dependent LSH for the original point set P, right? All the guarantees will be satisfied. So the main thing I need to make sure is that I have a function f like this. And I claim that such a function exists. I can construct such a function from average distortion embeddings. And like this, like D factor, like if I have an average distortion embedding with average distortion D, then with these properties here, I get something more like d log d as opposed to d. So there is some loss, which again, in some cases I can remove, in some cases I cannot. Okay. And good. So now, I think the last thing I will tell you is why does this have something to do with average distortion embedding? It's not quite the same guarantee, right? It says don't expand distances, but instead of asking that, instead of asking that that the average distance doesn't go down too much, I'm asking that something slightly different. If P is dispersed, so if there's no dense ball here, then there is no dense ball there. It turns out these are very similar guarantees. I'm not sure how much to go into this here. Yeah. So it turns out that these are very similar guarantees, and you can kind of go back and forth between them, at least up to like losing some log factors. So one thing that turns out is that you can assume that your original point set doesn't have too large a diameter, so the diameter is only like a constant factor bigger than your far distance CR. So that's already kind of pretty strong because you know that no ball of radius CR contains more than half the points, but you also know that the whole point set actually has diameter of maybe 10 CR. You can reduce to this case, a bit surprising, but you can reduce to this case because roughly speaking, you can show that like either something like this holds maybe after dropping some of the points in P, or you can give a very simple embedding, like a very simple F that does the job in the other cases. This very simple F is really just distance to some well-chosen set in the original space. So, okay, let's, not going into that, like, this is a bit fiddly, but it's not too hard. So let's maybe believe me that you can make a simplification. Then you're, like, from here, it's not too hard to show something. Not the best result, but you can show something. So now, once you reduce to this case, you just take F to be an embedding with average distortion D with respect to your points at P. Again, it may not be the original points at P because maybe in this reduction you drop some of the points in P, but more or less P. And now, because F doesn't expand distances by more than a factor of D, you know that F of P has diameter at most D times what it was originally. So now from 10 times CR, it became like 10D times CR. But at the same time, because P is dispersed, I know that the average distance in P is on the order of CR as well, right? Because there's no dense ball of radius CR. Okay. Right? And now from the average distortion guarantees of F, I know that the average distance in F of P is also in the order of CR. And if you look at these two, so FP has diameter dCr, like say 10 dCr, but the average distance is at least CR, you know that like a good fraction of the pairwise distances in FP must be at least CR as well. This is just like it's like a Markov type argument in a way, right? Right. So what you can get is that 1 over D fraction of the pairwise distances in FP are at least on the order of CR, which is enough to show that your point set is dispersed. Basically, a lot of pairwise distances being large is effectively the same as no ball having too many points, up to some loss in parameters. Okay, so that's the flavor of this argument. What you can get from this is that no ball of radius about CR in FP contains more than, okay, not half the points, 1 minus 1 over D fraction of the points, roughly speaking, maybe 1 minus 1 over 2D, something like that, which would give you worse results, but maybe gives you a flavor of how this argument goes. You can do better than this by kind of arguing more carefully on different scales. I won't go into that. Okay, so let me finish by just telling you what, okay, sorry, I'm a bit over time. Let me finish by telling you what the data structure at the end looks like. Okay, so far, let me back up. What did I show? I said that if I have a dispersed point set, I can more or less apply an average distortion embedding to it into L1, randomly partition in L1 using just a shifted random grid. And this gives me this data-dependent LSH like guarantee where close points collide, but my hash function, like my hash table doesn't have any really heavy bucket. Okay, So this is just a guarantee about dispersed point sets. What if I have a point set like this one that has some dense balls? Okay, so here's what the data structure would do. Let's say at first maybe this is a dense ball, but it's not quite dense enough to cause trouble. So this is still maybe counted as dispersed. So then I'll find data-dependent LSH partition, let's say into 2 parts, just to keep things simple. It could be into more than 2 parts. And I'll start building, roughly speaking, a randomized decision tree. So I'll partition my points into, let's say, the 2 parts, again, could be more, that are given to me by my data-dependent LSH partition, and I'll recurse on each. Okay. Once I do this partitioning, maybe now this cluster here became like too big, right? So now maybe this part I cannot really recurse on because it's not dispersed anymore. So I cannot apply the construction from before. So what I'll do instead, I'll just like remove this ball and remember 1 point from it. I'll just carve out this ball, remember 1 point from it, and store it here in this gray node. Okay, so this is what I'll call a ball node. It stores 1 point from this dense ball. And then I'll kind of recurse on the rest here. And maybe here this is dispersed and I can partition the same way as before. So here I just recurse on the remaining points here. Here I apply my LSH partition to build those 2 nodes. And maybe at some point I get to a part that has only 5 points, and then I can stop and just store the points. So that will be the data structure. At every point, if there is in building this decision tree, if there is a dense ball, I carve it out, and I recurse on the rest. If there is no dense ball, then I use my data-dependent LSH construction.
So when you say recursive, it means you just build a new data-dependent LSH to the subset.
Yeah, just build the tree like on the remaining points here. So here, now if the remaining thing is not dense, I'll somehow partition it. If it's still dense, then I'll still find the ball and carve it out. So I may carve out balls like multiple times. Okay. Good. So yeah, that's the data structure. Okay, I guess, yeah, here, I'm recursing, right? I'm partitioning into 2 parts. And now I have like few enough points here that I can just stop. Okay. So how do I answer a query here? I just follow the tree. So once I get a query, I say this is a query point. At every point in my tree, I follow where it should go. So it's above this partitioning line, so it goes here. At this point, if I have a bow node, I'm going to check. I will remember just 1 point in the bow node. I'm going to check, is the query point close to the ball, basically? Is it close to the bow node? If it is close enough, then I'll output the ball, like the point in the ball. If it's not close enough, I'll continue down the tree. And I either stop at a bow node because my query point is close enough to it, or I stop at a leaf where I have only like 5 points, and then I can find the closest neighbor among the 5 points by just looking for them. So that's the kind of data structure you get out of this. And the idea for like why this works, and this is where I'll stop, is okay. So the bow nodes are not a problem. Like they contain about half the remaining points. So I can carve out bow nodes like only like log many times. Okay, I don't have to worry about them. And if the query point is close to a point in one of those balls, then you're going to output something that's roughly close, right? So that part is not a problem. The randomized partitioning parts are like the place where you need to worry. But now, because I made sure that no part in my partition contains more than p2 fraction of the points, I can bound the depth of the tree. It's this, right? Like every time I do a randomized partition, no part in the partition contains more than p2 fraction of the points. So that's about how many times I would need to do this randomized partitioning. Okay. And now the analysis is simple. So say I have some near neighbor x star in P that's at most distance r from Q. So it's going to stay with Q together throughout all layers of the tree with probability at least P1 in each layer of the tree. And there are at most this many layers. And if you compute this, this is exactly n to the minus O of rho. So that's actually a similar argument to classical LSH arguments. Yeah, if like rho is something small enough, then this gives you like decent probability of finding your near neighbor. And now this is not like, this is not very high probability, so you just repeat the whole thing like about n to the rho times to amplify the probability of success. Okay, I'll stop here. All open problems we can talk about in the open problem session. Thanks. Sorry, I did take too long.
Okay, well, let's take time for one question before lunch, if somebody has one.
Yes.
Regarding the final data structure you described, I wonder, have you ever implemented it and can you run with the process?
No.
Why not? I think it's very efficient.
Could you? Yes. The question is if I have implemented the data structure, and the suggestion is that maybe it's already efficient. So for something like LP, maybe it's not terrible. But yeah, I don't know. I just haven't tried. Maybe with the right student, we could try. It'd be interesting. However, even for something like L2, I think LSH. I'm told LSH is not, like in most settings, somehow where people try to solve these problems. LSH itself doesn't seem to be like working as fast as they would like, and there's like other heuristic things that they don't have good worst case performance, but seem to work well for the kinds of inputs that people want to solve this problem on. So yeah, I'm not sure. Maybe I'm not sure what is the setting where it makes sense to try to implement these things. Maybe like a setting that people want to solve this kind of problem, but they just don't have a good data structure. And I don't know. There's this very different family of data structures, these like graph-based data structures. And in some sense, they seem to, they kind of make sense in any way to measure distance. It's not clear that they work well. We don't even know how to show, I guess, they work well, and they may not even work well for Euclidean spaces. It's not clear, what are the conditions under which they work well, I think, theoretically.
Those are, we'll talk later, but
You're
they're
not
not
completely
completely out of, instances, they're not completely different from what has been done in the community. For example, Robbie worked on navigating nets, and they're a little bit similar to navigating nets, for example, data structures.
Do you think there's any,
But I don't know, Robbie is in a better position to comment on it.
do you think it makes sense to try to implement this stuff for anything?
Well, here, two questions is, one is what is natural data set for LP? It is a problem that is solved a lot in practice, but standardly L2 is by far the most kind of important distance because most of the embeddings of objects is done using your deep neural networks, right? The output is an auto vector typically, right? So I don't know immediately what would be a natural data set where LP for P equals 4.
But it's not clear to me, do people always do L2 because that's what they know how to do, or is it because it's the right thing to do, right? I'm not so sure.
Of course, there is that.
Good question, yeah.
Yeah, I guess the other kind of empirical, some of the algorithms that empirically work very well are data dependent, but in a much more deeper way than here, in a sense, right? Where here it is data dependent, but in the sense it is a worst case statement for any data set which have performance of this sort. There are much fewer guarantees, but if a data set is very nice, then they work much better. Isn't the data dependent in the sense of beyond just having a worst case guarantee. So, but I think Petr will be talking about this in much better detail.
But I think I agree that the data structures don't seem fundamentally worse than LSH in terms of hidden constants or anything like that. Yeah, they probably are implementable. It's a good question how to evaluate them, on what data sets, what's the application where we need to go beyond L2. And